the Niranjan. Though the regression analysis is one of the most popular and widely used and applied statistical tool or econometric tool in economics research, but the use of that regression analysis in any economics research based on some assumptions. So like our own theories in economics, so every theory has applicable only in such given situations or the assumptions. The same is also holds good in case of the other disciplines, including in statistics. So though the regression analysis assumes several assumptions, or it is based on several assumptions. So totally there are 11 assumptions. I hope Professor Rangappa sir has given a hint on all those assumptions of classical linear regression model or the regression model in particular. So out of that 11 assumptions, fortunately, our data or the information which we have collected related to our variables to use regression analysis satisfies many of our assumptions. But the three important assumptions which are not met by our regression model due to because of some problems related to or pertaining to the data, and those three are, as you are noted in the morning classes. The one is the problem of multicollinearity. The second one is the problem of heteroscedasticity. And the third one is the problem of autocorrelation or serial correlation. The first problem, that is the multicollinearity, is related to the correlation among independent variables. And the second one is related to the variance of the error term, which, as of course in our regression analysis we have assumed that that is constant, but in most of the cases the regression results or the regression model violates that assumption. And the third is related to again to the error term, and in that series of assumptions of classical linear regression model, this assumption is the fifth assumption, that is no autocorrelation. No autocorrelation. And here in brief I will discuss this problem of autocorrelation and the nature of autocorrelation and the types of autocorrelation, the reasons for occurrence of the problem of autocorrelation in our regression model, that is causes of autocorrelation problem. So then the consequences of autocorrelation. Then the next is detecting measures, and the last but not the least is remedial or correction measures to autocorrelation. So if you get into any literature related to these practical problems of regression analysis, that is multicollinearity, then heteroscedasticity and autocorrelation, theoretically the literature is of course the framework of the literature or the framework for the discussion of these problems goes like this. That is the nature and types, causes, consequences, detecting measures or diagnostic tests, and the solution or remedial measures or correction measures. So hence, so my discussion also follows the same procedure which has been followed in the literature related to the problems of regression analysis, in particular to the autocorrelation problem. And let us first take the first content, that is the nature and type of autocorrelation. As just mentioned, this is the fifth assumption in classical linear regression model or classical normal linear regression model, which requires the observations on the error term, which is denoted as U, not to be correlated with one another. So, and one important point which you should have to bear in your mind, because the term correlation, the phenomenon correlation is not new to you, because you have been studied that concept in statistics. But the autocorrelation and the correlation are distinctly different, because the correlation measures the relationship of the two variables, two separate variables like x and y, or income and consumption, or investment and interest rate, and so on. The two variables which we have selected, and for those two variables we measure whether the variables are associated or not, related or not, or the degree of the relationship is measured by correlation. But the autocorrelation is the correlation for the same variable, for the successive values of the same variable, or it is successive values of the same variable, or the successive observations of the same variable. That's why you have only one variable. So for the same variable, you are measuring whether the successive observations of the same variables are correlated or not. So, and of course, here that variable, or the our variable related to this problem of autocorrelation, is the only one, that is error term. So hence our purpose of use of this autocorrelation in this regression analysis is to observe whether the successive values of the error terms are related or not, correlated or not. But the assumptions of the classical linear regression model that assumes the successive values of the error terms is not correlated. Hence, we can write in terms of expression this assumption of no autocorrelation as the covariance between ut and ut minus 1 is equal to 0 in case of time series data. So if our data is time series type of data, so then we can express this no autocorrelation as the covariance between ut and ut minus 1 is equal to 0. That means we are estimating the relationship, the correlation between ut and ut minus 1, and that correlation or the covariance is assumed to be 0. Whereas in case of cross-sectional samples or the cross-sectional data, then the covariance between ui and uj, and I hope you already noted the notations which have been used to represent the different types of data in econometrics. The T subscript is used to denote the time series type of data, whereas I or J are used to represent the cross-sectional data. So hence here UI is the one series of the error and the UJ is the another series of the error. Okay, now we are measuring the covariance or the correlation between these two. Again, the covariance between UI and UJ is equal to 0. So this is the assumption, or the fifth assumption, in classical linear regression model and also in classical normal linear regression model. But unfortunately, in practice, in many of the cases or in many of the situations, this assumption is not met by our regression model or not holds good in practice. So if this assumption is not holds good, then what we have? So we have a problem of autocorrelation. So that is expressed as the covariance between the ut and ut minus 1, and also the covariance between ui and uj in case of cross-sectional data is not equal to 0, which means there is a correlation between the successive values of the error term or the disturbance term. So if there is a correlation between the successive values of the error term, so then we call it is a problem of autocorrelation or a problem of serial correlation. So this is the meaning and the definition of autocorrelation or no autocorrelation and autocorrelation. Autocorrelation and no autocorrelation. And in another important point which you should have to bear in your mind, in use of regression analysis or econometric tools in any of our economics research, more specifically, for example, this regression analysis. So we call all these types of say the analysis or the work as model adequacy tests. Model adequacy test, whether our model is adequate or not, because we have several assumptions. So whether our assumptions are met by our regression model or not. So we can also call these as the model adequacy test. So of course, the model adequacy test is broader than these three problems, because in case of model adequacy test, you should have to test whether your disturbance term follows the normal distribution or not, because one of the assumptions in this classical linear regression model is the disturbance term follows the normal distribution. So along with that, every assumption we should have to test. If you test every assumption of that classical linear regression model, whether it is violated or met by our regression model, so that is called as model adequacy test. And our discussion, maybe this one and the last two previous sessions of Naranjan and Prem Kumar, is comes under that model adequacy analysis or model adequacy tests. So okay, so this is about the assumption and the violation of the assumption of autocorrelation. And I hope the Niranjan has already mentioned this. Though we have these problems, that is the problem of heteroscedasticity and problem of autocorrelation in general in a regression analysis. But in particular, if we observe, because it is based on the empirical works, it has been found that uh, more frequently we have a problem of autocorrelation in case of time series type of data, and whereas the problem of heteroscedasticity is more frequently found in case of cross-sectional type of data. So why we need these points? So because it is certain if you have a time series type of data, you should have to test, you should have to diagnose whether there is a problem of autocorrelation or not. If you have using cross-sectional data, you should have to certainly test whether there is a problem of heteroscedasticity or not. So hence, so if you have a cross-sectional type of data, certainly you have a problem of heteroscedasticity. And if the data you have been selected is a time series type of data, so certainly again you have a problem of autocorrelation. It doesn't mean that there is no autocorrelation problem in cross-sectional data, or there is no, say, the heteroscedasticity problem in case of time series type of data. So there are situations where you have a autocorrelation problem in heteroscedasticity and vice versa, cross-sectional data and vice versa. But in general, so always we have a problem of autocorrelation, or the problem of autocorrelation mainly related to time series type of data. So because of this reason, so our discussion will only concentrated on the autocorrelation problem in time series samples or time series type of data. That's why the next discussion related to the nature and the causes and the diagnostic tests and so on is only related to the time series type of data, or the problem of autocorrelation in time series type of data. So this is about the nature of the problem. That is the nature of the, in case of the nature of the problem, so we have defined what is autocorrelation. So then no autocorrelation and there is an autocorrelation. So then the types of autocorrelation. So like your correlation analysis. So even in your correlation analysis, you have type of correlations like positive correlation, negative correlation, simple correlation, multiple correlation, isn't it? Linear correlation, non-linear correlation. So these are the types which have been studied in statistics related to correlation. So even in case of autocorrelation problem, we have some types. So the first type of the autocorrelation is classified as the pure autocorrelation and impure autocorrelation. The pure autocorrelation is also called as true autocorrelation. The impure autocorrelation is also known as false autocorrelation. So hence the first classification of the types is the pure and impure, are true or false. True or false. So the pure autocorrelation is caused by the violation of assumption number 5. So if the error terms are autocorrelated, then we have a pure autocorrelation. So if ut and ut minus 1 are autocorrelated, If uj and ui and uj are autocorrelated, or the covariance between these two exists, then we call that autocorrelation as pure autocorrelation or the true autocorrelation. But there are some situations where our regression results show up that there is a problem of autocorrelation, but in actually it is not. So that is called as the impure or false autocorrelation. So that's why the false autocorrelation or impure autocorrelation is caused by something that shows up as though assumption 5 is violated, even though it is not, even though it is not. So actually, in other words, actually there is no autocorrelation problem in our regression model, but the results show you that there is a problem of autocorrelation. So hence it is a false autocorrelation or impure autocorrelation. So this is the first classification or the first type of autocorrelation. The second type is related to order of the autocorrelation. Based on the order of the autocorrelation, so we have first order autocorrelation and higher order autocorrelation. So here order refers to the correlation between the successive values of the error term. Earlier I have told you to define the autocorrelation problem, but how many successive values of the errors are taken into consideration in calculation of autocorrelation, and that number of the error successive terms determines the order of the autocorrelation. For example, the first order autocorrelation is represented as follows. That is ut, which is equal to rho. This is a Greek alphabet, rho, ut minus 1 plus vt. So now of course we have an expression like this. So in case of this expression, so we are estimating autocorrelation, that is whether ut depends upon its own one period lagged value. So t minus 1 in econometrics is called as one period lag. So lag means, of course, time. That means, so the current value of current value of ut depends upon its own previous value. In this case it is one period lag. So if we have expressed the relationship between the two errors, one is ut, the other one is ut minus 1, in this form, this is called as the first order autocorrelation or first order Markov process. Markov, the name of a statistician. So Markov process, and in literature it is denoted and called as AR1. That is autoregressive order 1. You should have to read it as autoregressive order 1. So it is order 1 because you are calculating autocorrelation for selecting only first order, or by taking only t minus 1 for the error term, that is ut minus 1. And the third element in case of this expression is vt. This vt is the error term of this first order autocorrelation. So this error of this autocorrelation function, you can also call it as an autocorrelation function. So the error term of this autocorrelation function satisfies all the assumptions of your classical linear regression model. This is the another important point which you should have to bear in your mind. The first is you are testing whether the ut, the error value, depends upon its own past value or not. For that you need an error term in regression analysis. Now we have a new error term that is denoted or represented as vt. This error of this autocorrelation function satisfies all the assumptions of classical linear regression model, and most importantly related to it are the expectation of vt is equal to 0. So that is the third assumption. That is the mean value of the disturbance term is 0. So here the VT is the disturbance term of this autocorrelation function. Hence the mean value, that is expectation, is a mathematical expectation which is equal to mean in statistics. So hence expectation of VT is equal to 0. Then the second related to homoscedasticity and the third related to autocorrelation problem. So that means your disturbance term of the regression model as the problem of autocorrelation, but the error term in your autocorrelation function is not having any these issues, or that satisfies all the assumptions of classical linear regression model. So this is called as first order autocorrelation. First order autocorrelation. This is the amount in the second classification. Then the higher order means, so you have to include the more number of lagged values of the error term into your right hand side of the equation. So involves the process in which the error term depends on its own 1, 2, 3, and so on previous period lagged values. For example, the second order autocorrelation is denoted by AR2, which is represented as follows. So ut is equal to ρ1 ut minus 1 plus ρ2 ut minus 2 plus Vt. So now it is 2 because you have been included the two period lagged values of ut, that is ut minus 1 and ut minus 2, and the ρ1 and ρ2 are the coefficients of the first order and second order autocorrelation, and of course this is the coefficient of this autocorrelation function. So that gives you the magnitude, the degree of the autocorrelation between ut and ut minus 1, ut and ut minus 2, and so on in case of higher order autocorrelation. So the higher order autocorrelation means we are estimating, or we have expressed our the disturbance term depends upon the more number of lagged values, or the higher number of lagged values, or the past values of the ut. So hence we call it as higher order autocorrelation. So that is related to second classification. First classification is related to pure and impure. The second one is related to the first order autocorrelation and the second order autocorrelation. The third classification is positive autocorrelation and the negative autocorrelation. So this is somehow equivalent to your positive correlation and negative correlation. So now we have a positive autocorrelation and negative autocorrelation. This is related to your estimated value of the raw. So in case of the positive autocorrelation, the raw indicating the errors given in a sign are generally followed by the errors of the same sign. That means if you are calculating the raw, if that raw estimated value of the raw is plus, then the successive values of that raw for a specific range of values is also positive. So by observing this figure, for example, so from year to year, the values of this raw is positive. Hence, that has goes on increasing. But from year to year, in the first turn, that has been taken by this curve, from year to year, negative. So negative in the sense that has been declining. So that means the sign of this raw as the same sign. Positive values followed by positive values, negative values of the raw followed by the negative values. That's why if the raw as, or the sign of the raw as positive values followed by the positive values, or the negative values followed by the negative values, we call it as a positive autocorrelation. Positive autocorrelation, that can also be seen from one more diagram like this. This is positive values followed by positive values, negative values followed by negative values. That means, so the value of, that means when the value of the ut increases, ut minus 1 also, when the value of the ut minus 1 increases, ut also increases. If the value of the ut minus 1 decreases, the values of the ut also decreases. So that's why we call this as a positive autocorrelation. So whereas in case of the negative autocorrelation, one is positive, the other one is negative. For example, if ut minus 1 is positive, ut is negative, and vice versa. So that's why frequently this curve, of course, the residual curve, this is the diagrammatic representation of the ut estimated value of the disturbance term. So that frequently crosses the zero line. So one is positive, the other one is negative. Positive, negative, almost positive, negative, positive, negative. So that's why we have an opposite signs, opposite sign. If one is plus, the other one is negative. If the ut is plus, the ut minus 1 is say negative. So if the ut minus 1 is plus, ut is negative. So like this, if the row is negative, so that the errors of a given sign are generally followed by the errors of the opposite signs, then we call it as a negative autocorrelation. So the same is represented in one more graphical representation is like this. So let us observe the first the dotted points like this. So if the ut is ut minus 1 is negative or positive, then other one is negative. The next value is positive, then the fourth one is negative almost. So like this, there is the successive values of this error term that changes the signs. So then we call it as the negative autocorrelation. Negative autocorrelation. This is the third classification of the types of correlation. That is, the first one is related to the pure and impure correlation. The second one is related to first order and higher order correlation, and the third one is related to positive correlation and the negative correlation. And related to this positive and negative autocorrelation, the point which we need to bear in our mind in econometrics, more specifically in case of the time series type of the data, is always related to positive autocorrelation. Positive autocorrelation. So our discussion in this class, and also in most of the practical works also, the problem of positive autocorrelation is more important for us than the negative autocorrelation, because the negative autocorrelation in case of the time series macroeconomic data is typically a sign of model mis-specification. So that means, so if there is a negative autocorrelation in our regression model, it is not because of the data, it is not because of the time series type of data, it is because of the mis-specification of your model. So mis-specification refers to whether either your functional form is not correct, or you have omitted important variables, or you have included irrelevant variables. So because of this mis-specification of your model, you have a problem of the negative autocorrelation or negative autocorrelation presence in your model due to because of this mis-specification of your model. So hence our discussion, or even in the literature, so the dealing with the problem of autocorrelation is not related to that problem of negative autocorrelation. It is only related to positive autocorrelation. So that's why earlier I have told you that in most of the cases, our discussion in related to autocorrelation is related to only time series type of data rather than cross-sectional data. In the next important point is within the types of the data, within the types of autocorrelation problem, especially related to positive and negative autocorrelation, our discussion is only related to positive autocorrelation, not to the negative autocorrelation, because the negative autocorrelation is not because of the data, not because of the error term, it is because of the mis-specification of the model. Hence our focus is here only with time series type of data and only positive autocorrelation in time series type of data. Okay, so that is related to the types of autocorrelation. And in related to this positive and negative autocorrelation, related to the magnitude or the degree of the autocorrelation, and you know that the correlation value always lies between -1 to +1. The same rule is also holds good in case of this autocorrelation problem. Hence the estimated value of the raw from that autocorrelation function that lies between -1 to +1. If the raw is equal to -1, we call it as a perfect negative first order autocorrelation. If the raw is equal to 1, we referred it as a perfect positive autocorrelation, like your perfect correlation and perfect positive correlation, perfect negative correlation. So the same kind of interpretation we hear for this autocorrelation. -1 refers to perfect negative first order autocorrelation, and the plus value, plus one value for the raw, that indicates, okay, the perfect first order positive autocorrelation, first order autocorrelation. And in case of the raw which is equal to 1, the first order Markov process or the AR1 process becomes like this. So because we have earlier represented this equation as ut, which is equal to raw ut minus 1 plus vt. So since the value of raw is equal to 1, you need not to write that 1 here, because 1 into t minus 1 is same as ut minus 1, because anything multiplied by 1, so the value of the element does not change. That's why our ut is equal to raw ut minus 1 plus vt. Now we can be written it as ut is equal to ut minus 1 plus vt when the value of raw is equal to 1 in case of first order Markov analysis. So this is known as, of course, the random walk, and I hope you will discuss, or you will not or learn about this. You learn about this random walk in the next classes, especially I think from Prem Kumar. So, and this process is random walk, which is one of the most important characteristic which have been found in time series type of data. So what is that, and how to deal with that, and how to correct it, I think you will discuss in that particular class. So, but in time series analysis, this is another important, or in case of the time series type of data, so this is the random walk is actually related to this the raw value, or related to positive or negative value of the autocorrelation, more specifically related to the positive value of the autocorrelation. And if you have such a situation, that is ut is equal to ut minus 1 plus vt, when where the raw is equal to 1, so that is called as the unit root problem in time series type of analysis. Okay, so this is just related to the classification of or the types of autocorrelation. Then related to random walk process, I don't want to get into that. So you will learn all these in case of the time series econometrics. So that is related to types. Okay, in case of types, we have three important types. The one is pure and impure. The second one is first order and higher order. The third one is related to the positive or and negative autocorrelation. Okay, then by having the knowledge of this nature and the type of autocorrelation, okay, the types of the autocorrelation, so then the next question which arises in our mind is that, so why this problem is present in our regression model, why it arises in our regression model. So there are different reasons for this. And since we have started our discussion related to classification into impure and pure autocorrelation, as already I have told you that the reason for the presence of autocorrelation problem in the impure autocorrelation is the mis-specification of our regression model. The mis-specification, as I already told you, that includes the three important concepts. The one is omission of the relevant variable, or the incorrect functional form, or the third one is including a irrelevant variable. So even in case of including an irrelevant variable, so we call it as a mis-specification of our regression model. So hence the impure autocorrelation is only caused by the model mis-specification in terms of omission of relevant variable, or specification of the functional form, or the incorrect functional form. And the third one is including a irrelevant variable into our regression model. And as I already told you that our discussion is not related to that impure autocorrelation problem, because if you go with that impure autocorrelation, we have to take into account that model specification. So model specification means that what model we should have to develop, what are the say the constituents of in econometric model, so how to build a model. So they are the part of that specification of econometric model. So hence I don't want to hence I don't want to take into that. Okay, so then the next hence our focus, as I already told you, is related to only pure autocorrelation problem. And the causes for, or the reasons for this pure autocorrelation are as follows. The inertia or business cycle phenomenon, the cobweb effect or the lagged response type of models, and the autoregression type of models, and the data messaging. So these are the four important reasons, or because of these four important reasons, so the pure autocorrelation is present in our regression model. So let us briefly discuss each of these uh, one by one, or the reasons for this pure autocorrelation. As all of us knew that the business cycles or the business cycle phenomenon, um, that has been exhibited by the most of our time series type of data, where we have a cyclical pattern of our time series type of data. Uh, the pattern which follows by our economic variables, especially the macroeconomic variables, are in cyclical in nature. So one period they will rise, another period they will falls. So that's why always we have such a cyclical in nature. So if we have been observed that cyclical characteristic of our macroeconomic type of data, so naturally if there is an increasing in one variable, the related variables are also increases due to because of that kind of relations between our economic variables. Or in other words, so if one variable increases, the most of the related variables which are positively related with that particular variable also increases. If a particular or a major variable start to decline, then the other related variables are also decreases. So this phenomenon we call in economics as business cycles, are the cyclical pattern of our time, our economic time series. So because of this reason, so the correlation appears, or the autocorrelation present in our regression model. The second one is the cobweb effect. So this type of cobweb effect is very familiar in case of agricultural products or supply of agricultural products. So because the any decisions regarding the crop decisions or growing crops, that depends upon the previous information. That is, for example, what to grow or which crop to grow in this period depends upon the prices of that particular crop in the previous period. Hence we should have to include the lagged values of the variables into our model. So since we have included the lagged values of the variables into our regression model, that causes the problem of say the autocorrelation. For example, supply of paddy in 2020. So the supply of paddy in 2020 depends upon the price of paddy in the previous season. So that's why that is PT minus 1. So the supply of paddy is ST, whereas the price is not PT. It is the PT minus 1. So this is called as cobweb phenomenon or cobweb effect in agricultural economics. So that due to because of that cobweb effect also, so we have a problem of autocorrelation. Then autoregression. This autoregression is like a dynamic nature of econometrics. So where the dependent variable appears, or the past values of the dependent variable appears as the one of the independent variable, or the lagged value of the dependent variable appears as independent variable. For example, here you have a model like this. YT not only depends upon XT, also depends upon its own previous one period lagged value, YT minus 1. By incorporating the lagged value of the dependent variable into your regression model, that causes the problem of autocorrelation. And this is the third reason for the problem of autocorrelation. And the fourth and the last but not the least one is the data manipulations. So due to because of this data manipulation, which need to be used in case of econometric estimations, so that can increase the likelihood of autocorrelation. The data messaging or data manipulation includes like smoothing, seasonal adjustment, moving averages. So that means if there is a wide or a high fluctuations, high variations in your data, so we need to reduce that variations. So if we need to reduce that variations, smoothen that variations, so that they are called as smoothing techniques. So if we use that smoothing techniques, so that creates the problem of autocorrelation. Because so let us take an example. So if you take the inflation rate, weekly inflation rate, if you take the weekly inflation rate, okay, so then monthly inflation rate, then quarterly inflation rate. Just observe the graph of these three inflation rates. So the commodity is same, or if you taken the inflation rate at the India level, okay. So if you have been observed this, if you the more fluctuation is variations is found in case of weekly inflation rate compared to other two. So the monthly inflation rate is more smoothened compared to weekly inflation rate, whereas the quarterly inflation rate is more smoothened compared to these two. If you take annual inflation rate, that more or less like almost a straight line, So we know that. So if that variation reduces, or if you smoothen your variables, that leads to increase the relationship, or correlation increases, or the association increases. So hence, because of this data manipulations, we have a problem of this autocorrelation problem, either through seasonal adjustment or through moving average. Moving average is also a method of smoothing techniques. Exponential smoothing is one smoothing techniques. Okay, so any kind of these smoothing techniques, so that lead to the problem of autocorrelation. So these are the main causes for the problem of autocorrelation. So that's why we should have to be careful in our mind, be careful in use of this time series type of data regarding um, this problem of autocorrelation. So if you have used the smoothing techniques, if you have used seasonal adjustment or smoothen your techniques by moving average, so certainly you have a problem of autocorrelation. So they are related to the autocorrelation problem, causes for the autocorrelation. So in case of causes for the autocorrelation, we have the four important causes. The first one is related to business cycles. The second one is related to Cobb phenomenon. Then the third one is related to autoregression, and the fourth one is related to data manipulations or data messaging. These are the four important causes for the problem of autocorrelation. And the next is the causes of the consequences of autocorrelation, or the implication of the autocorrelation problem. This autocorrelation problem, or the consequence of the autocorrelation problem, more or less similar to the heteroscedasticity. So there is not much difference between the consequences of heteroscedasticity and the consequences of autocorrelation problem. Hence, I need not get into this again, because the Niranjan, I hope, has already discussed about the consequences of heteroscedasticity. So to have a look on this, one of the most important, the point which we have of course noted in use of regression analysis in practice, with an assumption that our OLS estimators, that is the beta 1 hat and beta 2 hat and so on, are assumed to be blue, the best linear and biased estimators. So our regression results, or our regression estimators, are best linear and biased estimators only when the assumptions are met by our regression model. If our assumptions are not met by our regression model, so then you cannot say our OLS estimators are best linear and best estimators without checking that, without testing that. So hence the implications or the consequences of violations of these assumptions of the classical linear regression model, including autocorrelation, is related to whether our OLS estimators are continue to be the best linear and biased estimators or not. Generally, if a regression model has a problem of autocorrelation, So then our OLS estimators are not blue. Our OLS estimators are not best linear unbiased estimators. So our OLS estimators are not best estimators. Best estimators. So of course the consequences are related to why our wireless estimators are not best in the presence of autocorrelation. So let us have here, here we have few points related to that consequences. Though there is a presence of autocorrelation, our OLS estimators remain unbiased and consistent. Remain unbiased and consistent. I hope you already noted that blue properties of the OLS estimators are the Markov theorem, okay, of that OLS estimator. That is unbiasedness property, then minimum variance, then consistency property, then okay, and also the mean square error is minimum, and so on. These are some important properties. Due to because of these properties, we call our OLS estimators are the best linear unbiased estimators. So out of that properties to say our OLS estimator as the best estimators, so the our OLS estimators are continue to be unbiased and consistent even if there is a presence of autocorrelation. But in case of the positive autocorrelation, the true variances of these estimators become larger than when there is no autocorrelation. So related to the variances of these OLS estimators, the values of the estimated values of the variances are larger than when there is no autocorrelation problem. That's why the effect, the impact, or the consequence of the presence of the autocorrelation is on the variances and the standard errors of the OLS estimators. The values of the standard errors or the values of the variances are larger when there is a presence of autocorrelation. So due to because of that larger variances of the OLS estimators or the beta, they are underestimated. Then the variances of the beta hat would be underestimated, even though the true variance of the beta is now larger as result the positive autocorrelation. So due to because of this underestimation of the variances of the OLS estimators, the true value of the disturbance term variance. So this is sigma square hat. This sigma square hat refers to the estimated value of the variance of the disturbance term, or it is the variance of the disturbance term. The variance of the disturbance term is estimated by making use of this formula. That is also underestimated. This is also because of the consequence of presence of that is autocorrelation. The first one is the variances of the standard, the variances of the betas are larger, they are underestimated. Then the true value of the sigma square is also underestimated. Because of these results, the T and F test would be unreliable in the following sense. So you cannot believe on your T test and F test because of this underestimate of the variances and the underestimate of the sigma square, that is the population variance of the disturbance term. So because of this standard error of the beta hat is underestimated, the beta is unbiased and the T ratios are overestimated by yielding more confidence than warranted. So that provides you a larger confidence because I hope you know the concept of confidence interval. So your confidence interval become larger because of a larger value of your standard error, which is underestimated. So though there is a larger value, but the standard errors are underestimated. Because of that, you have a larger confidence, so which is larger than we have warranted or we have expected. Similarly, all F statistics as well as your value of the R square, adjusted R square, will be overestimated because in calculation of this F statistics, R square, adjusted R square, the variances are being used, the standard errors are being used. So because of this, so the F statistics is also overestimated. So because of these consequences or because of these reasons, the probability of committing type 1 error will be higher when OLS is used in the presence of the positive autocorrelation. I hope you know the meaning of type 1 error. Type 1 error means rejection of a null hypothesis even though it is true. You are rejecting a true null hypothesis. You are rejecting a true null hypothesis, or you are committing an error of rejecting a true null hypothesis due to because of the presence of positive autocorrelation. So as just I have told you that these are almost the same consequences as you are already noted in your the consequences of heteroscedasticity. So because of these consequences, everyone who make use of this regression analysis, more specifically for the time series type of data, has to test the problem of autocorrelation, whether our regression model is suffers from the problem of autocorrelation or not. So otherwise the results are not reliable. So due to because of the points thus far we were discussed. So that's why this is related to the consequences of the autocorrelation problem. Consequences of the autocorrelation problem. So, okay, then after having the knowledge of these consequences, since the consequences are severe, the severe in the sense that our OLS estimators are not best linear unbiased estimators, and our F test is not reliable, our T test is also not reliable, our goodness of fit, that is R square and adjusted R squares, are also not reliable. So which implies that our regression itself is not reliable. Our results are not at all reliable, are not valid. So hence we should have to check, we should have to test whether our regression model plugged with the problem of autocorrelation or not. So without testing that, we cannot directly uh, take our results as good results, or we cannot interpret our results without testing autocorrelation, diagnosing autocorrelation. There are different methods of diagnosis. I hope both Prem Kumar and Niranjan has mentioned or told you that why we have several diagnostic tests, several solutions or correction measures. So the reason for having more than one diagnostic test, more than one correction or say the solution or the remedial measure for all these problems of regression analysis, the reason is that due to because of the data. And all these problems, whether you have a problem of multiple linearity, the problem of heteroscedasticity, the problem of autocorrelation, all these problems are related to data. That means related to sample, not related to the population. Since from one sample to other sample, the values are changing or the sample characteristics changes, and we call in statistics this as the sampling fluctuations. So because of these kinds of sampling fluctuations, so anyone cannot find a single solution or single detecting method to detect any problems or any of these problems. So because of these reasons, so we have several rules of thumbs. Actually they are called as rules of thumbs for detection, and the rules of thumbs for the solution. Rules of thumbs for detection and rules of thumbs for say the solution or correction measures. So let us take the most important the rules of thumbs or the detection measures or the diagnostic tests of autocorrelation. So the two most important of course uh, the detecting measures of autocorrelation that is routinely reported by the most of the statistical package is Durbin-Watson test or the DW test or the D test, simply D test, and other is the LM test. That is the most popular Durbin-Watson test. So in my discussion I will only take these two methods of detections of autocorrelation. One is DW test, the other one is LM test, Lagrange multiplier test or Godfrey Bruce Godfrey test. test or the BG test for say this autocorrelation. So let us first take the DW test. Just I have mentioned that this test is most popular test of first order autocorrelation. First order autocorrelation, and it is a pure autocorrelation, as I already told you that. So to use this first order autocorrelation test of DW test, our regression model should satisfy the following conditions, or rather we can call this as the assumptions of DW test. So if these assumptions are not holds good, then you cannot use the DW test as a detection measure of autocorrelation. The first one is the regression equation should contain any intercept. That's why in your regression equation there must be intercept term beta naught should be there, or beta 1 should be there. If it is beta 1 and beta 2, or beta naught and beta 1, so your model should consist of intercept term. The second one is the independent variables should be non-stochastic. Non-stochastic means they are fixed, given. They are fixed, given. If they are not fixed or given, they are called as random independent variables. Random independent or stochastic independent variables. So if your independent variables are stochastic, then you cannot use, yeah, that is the Durbin Watson test for the autocorrelation. And the third one is the model is not autoregressive. That means the lagged value of the dependent variable should not be in your regression model. That is why t minus 1 should not included in your model, or why t minus 2 should not included in your model. That is called as lagged value of the dependent variable. So if you include a lagged value of the dependent variable as one of the independent variable or variables, then we call it as a autoregressive model. But for application of this Durbin-Watson test, the model is not autoregressive. Then, as we already noted that this test is only used for AR1 pattern, that is autoregressive order 1, and the last but not the least is the error term should be normally distributed. These are the conditions to use the Durbin-Watson test in our regression model. And how this Durbin-Watson D test was developed by Durbin and Watson. So here we have a brief discussion on that. The Durbin-Watson D statistic is defined as it is the sum of the squares of the differences in the values of the error terms divided by the sum of the squares of the disturbance term. So this is the interpretation for this elements of the Durbin-Watson statistics, or the D statistic. So UT is UT hat. Of course, I hope you know that once you put a hat or a cap on any element or a variable in econometrics or statistics in general, that is estimated because the true values of the populations are not estimable, or they are not observable. U is not observable. Hence, we have to observe the U from it estimated, that is the U hat. Of course, the same is also holds good here. That's why UT hat minus UT minus 1 hat. You should have to take the difference between these two. The difference is squared, and that squared difference is summed. This is the numerator. The denominator, you have an estimated value of the disturbance term that is squared and summed. So then finally you should have to divide one by the another. And UT hat, as I already told you, that it is the estimated value of the disturbance term by making use of OLS, or they are called as OLS sample residuals. By having some mathematical relationship between our earlier coefficient of that autocorrelation, that is rho, with this Durbin D statistics, we can approximately represent the relationship between these two as follows. And normally this is true only for the large samples. That is the D approximately equivalent to 2 times of 1 minus rho hat. So that means, let us assume that you have estimated already UT is equal to rho UT minus 1 plus VT regression. And by regressing that, you are able to obtain rho hat. So once the rho hat is known to you, you have to subtract that estimated value of the rho from 1 and multiply the difference with 2. that gives you the D statistic. So now you are able to obtain this D by using the wireless residuals like this, or the raw height by using this expression. And as I already told you that the raw height is an estimator of the raw, that is autocorrelation coefficient. Autocorrelation coefficient. And suppose we want to test the null hypothesis of no first order autocorrelation, then your null hypothesis is written as H naught, where rho is equal to 0, against an alternative hypothesis of H1, where rho is not equal to 0. The rho is equal to 0 means no autocorrelation. Rho is not equal to 0 means you have a problem of autocorrelation. Then based on that calculated D value, that is the Durbin-Watson D statistic, if this Durbin-Watson D statistic is closer to 2, closer to numerical value 2, when this Durbin-Watson value closer to 2, when the rho is close to 0. When your estimated raw value is close to 0, then your D value is closer to 2. Then less likely you are to reject your null hypothesis. That is, you are conclude that. Okay, like most likely you have to conclude that there is no statistically significant evidence of AR1 in your data, or there is no autocorrelation in your data. Or from this point, what you should have to bear in your mind, if your calculated value of the Durbin-Watson statistic or the D statistic is 2, which is an indication of there is no autocorrelation. The next is when your D is closer to 4, more likely it is that there is a negative first order autocorrelation. So hence, if your autocorrelation, your calculated value of the D is closer to 4, which is an indication of negative autocorrelation. Then finally, if your calculated value of the D is closer to 0, then it is more likely that there is a positive first order autocorrelation in your problem. And hence, if your calculated D is closer to 0, which is an indication of positive autocorrelation. Hence, now we have 3 values. The one is 2, the second one is 0, and the third one is 4. So by observing these 3 values, we can now express like this, or we can write this, say the Durbin-Watson value like this. The Durbin value lies between 0 to 4. That is, the minimum value of the Durbin-Watson statistic is 0, and the maximum value is 4. So, and the middle of these 2 is 2. The 2 indicates no autocorrelation. If your calculated value of the D statistics is closer to 0, indicates positive autocorrelation. If your calculated value of the D is closer to 4, that indicates negative autocorrelation. So this is a discussion related to the range of values taken by the Durbin-Watson statistic or D statistics. But the question is how close the close is. Whether 1.9 is close to 2, whether 1.8 is close to 2, 2.1 is closer to 2, or 0.8 is closer to 0. So we cannot decide that, or we cannot draw any conclusion just by the above 3 statements: closer to 2, closer to 4, closer to 0. We cannot conclude there is no autocorrelation or a positive or negative autocorrelation based on only the above points. So hence, to decide how close the close is, the Durbin-Watson themselves have developed a table for that, or the Durbin-Watson statistic for that. So the reason is this Durbin-Watson D statistic not follows the standard distributions. Not follows standard distributions means that D not follows T distribution, or chi-square, or F, or the normal distribution. So hence this D is not follows any standard distributions. the Durbin-Watson themselves have developed one distribution for that, and the distribution is called as Durbin-Watson distribution. And based on that Durbin-Watson distributions, by using simulations of or Monte Carlo simulation, of course, they have developed the Durbin-Watson tables, and also identify the statistics or the probability values from that Monte Carlo simulations, and they provide us the critical values for us. But unfortunately, the Durbin-Watson statistics, okay, given by the Durbin-Watson themselves, does not have any unique critical values. So unique critical values means you have a typical value, single value of a specific value to reject your hypothesis of no autocorrelation against the presence of autocorrelation, and so on. So in case of, for example, t-test, or in case of f-test, in case of normal distribution test, and so on, you know that if your calculated value is 3, whereas the table value is 2, so you have a specific value, you have a unique value, because the at 5% level, for example, in case of standard normal distribution, it is 1.96. So if your calculated value is greater than 1.96, you can reject your null hypothesis. Hence 1.96, a critical value which is unique, but there's no question of that uniqueness in case of Durbin Watson test statistic. That is the unfortunate thing of the use of this Durbin Watson test. Okay, so then how this Durbin Watson statistics works, or how does this the D statistic has been developed. So here we have a procedure for that. To use this Durbin Watson test, we should have to first estimate the regression equation. Then we should have to retrieve the values of the residual sample residuals. Then by making use of that sample residuals, we have to calculate D statistic. That's why D is equal to sigma within the bracket ut hat, and so on, So by first you should have to estimate your regression equation, then calculate the Durbin-Watson D statistics from that, then choose the level of significance. That is one of the important point which we needed to test any hypothesis. It is whether you are testing your hypothesis of no autocorrelation at 1%, 5%, or 10% level. That's why choose a level of significance, and then look up the Durbin-Watson table for that, then DU and DL. So this is the unfortunate thing. That means there is no any unique value. You have two values. One is upper value, other one is lower value. DU refers to upper Durbin-Watson value. DL refers to the lower critical value of the Durbin-Watson table, and given the sample size n and the number of the slope parameters in your model. So that's why this is cumbersome, complex. So whereas in case of your other standard hypothesis testing, what you required is only degrees of freedom in hypothesis testing, except in case of your standard normal distribution. But along with that, you need lower level of Durbin-Watson, upper level of Durbin-Watson, and the number of the slope parameter. That is the betas you need to estimate, except your intercept. So because for every of these, your Durbin value changes in the Durbin value table, or the critical value changes. Hence somehow it is a cumbersome procedure, and these are the rules which have been used in Durbin-Watson analysis or test for two-tailed test and one-tailed test. Okay, two-tailed test and one-tailed test. This is for the two-tailed test, and for the diagrammatic representation of this two-tailed test is like this. As I already told you that the Durbin-Watson value lies between 0 to 4. The middle of that is, or the range is 2. So if the rho is equal to 0, no autocorrelation. So if this calculated value of the rho is closer to 0, means rho is greater than 0. Rho is greater than 0 means it is a positive autocorrelation. So if the calculated value of the D is closer to 4, the rho is negative, means less than 0. It is a negative autocorrelation. So, and if one of the most important limitation, of course, of this the Durbin-Watson test is that, so there are two areas here with the question mark. This question mark is known as inconclusiveness. Inconclusive means you cannot make any conclusion whether to reject your null hypothesis or not to reject your null hypothesis if your calculated value lies between dl to du in this part, or 4 minus du and 4 minus dl in this part. So that's why the use of this Durbin-Watson statistics, as it already noted in the conditions, it has several conditions to use this. If one of those conditions are not met by our regression model, you cannot use the Durbin-Watson test. Along with that limitation, the most important limitation is this inconclusiveness. That means if your calculated value lies between du to dl, dl to du, and 4 minus du to 4 minus dl, so you cannot make any conclusions regarding reject or not to reject your null hypothesis. And in case of the one tail test, the same, earlier we have noted that the same type of problem we have. So this is about, I think, the Durbin-Watson test. And just I have told you that, so because of that several conditions to use this Durbin-Watson test, that is not much used in practice. And the most important limitations of the use of this Durbin-Watson test are as follows. As we already noted, that is applicable only to first order autocorrelation. If the autocorrelation is present in the higher orders, that is ut minus 1, ut minus 3, ut minus 4, and so on, you cannot use Durbin-Watson test to test the autocorrelation problem. And also, if your model include a lagged value of the dependent variable, if your model include lagged value of the dependent variable, you cannot use Durbin-Watson test. That is, does not apply to the autoregressive models. And the third and the most important one, as I just told you, it can be inconclusive. That means that question mark area is the areas of inconclusiveness. So if your calculated value lies in that particular area, so that area is called as an area of inconclusion, then you cannot make any decisions regarding the presence or absence of autocorrelation. So this is about the autocorrelation, that is the Durbin-Watson test and the limitations of Durbin-Watson test. So because of these limitations of Durbin-Watson, the two econometricians named Bruce and Godfrey developed an advanced test over that Durbin-Watson, which overcome all the problems earlier we have noted. That means we can use this LM test or the Bruch-Godfrey test, okay, BG test, for higher order correlation, and it never inconclusive, and it applicable both for autoregressive and non-autoregressive. Hence, the BG test is so familiar and popular, and this is generally called in literature as LM test, because it is based on the Lagrange multiplier kind of process or the procedure. That's why it is called as LM test or BG test. Okay, BG test. Then how this BG test works, or what is the procedure of this BG test? Let us assume that you have a regression model like this. This is a multiple regression model. It is a multiple regression model. So in case of this multiple regression model, it is the pth order multiple regression model. That means you can have any number of autocorrelation terms in your regression. So then how it works? First, you should have to estimate your model, that is the multiple regression model, retrieve the residuals, obtain the residuals, that is UT hat. Then use these estimated values of the UT and as a dependent variable on the independent variables of the original form. Then UT lagged ones through the P periods. That is, along with your independent variables, you can use UT minus 1, UT minus 2, and UT minus 3, and so on, UT minus P. That is the pth order. Okay, pth order of autocorrelation. Pth order of autocorrelation. So, for example, if you have used only P is equal to 1, the order is AR1. So, if you use 2, that is equivalent to autoregressive order of 2. So that means you can use this to test for any order of the autocorrelation. So the right hand side variables are original independent variables along with the lagged values of the disturbance term or the estimated value of the error, that is UT. That is the second step. In case of the third step, your null hypothesis is no pth order autocorrelation. No pth order means first order, second order, third order, fourth order, and so on. Any number of orders you can test for the problem of autocorrelation. So the parameters of these UT minus 1 or the lagged values of the disturbance terms are, let us assume that alpha 1, alpha 2 and also so on to alpha p, which is assumed to be 0. That means there is no autocorrelation because ut is not ut minus ut is not correlated ut minus 1, ut is not correlated with ut minus 2, ut is not correlated with ut minus 3, and so on, so on. So hence you have to pick the parameters of or the estimated coefficients of the lagged values of the disturbance term, and they are assumed to be equal to 0. If they are assumed to be equal to 0, then your assumption is, or your null hypothesis is, there is no autocorrelation. And you should have to use a new test statistic here. The new test statistic is n minus p times r square. N is the number of the observation or sample size, minus p means the number of the orders you have been used. This difference should be multiplied with the estimated value of the r square from the previous regression. As this is a test statistics. Earlier I have told you that this test statistics. Earlier I have told you that. Okay, earlier I have told you that, and this test statistic follows chi-square distribution, and hence you should have to look into chi-square distribution table and compare this test statistic or the calculated value of this with the chi-square distribution value with the p degrees of freedom. So if your calculated value of n minus p times r square is greater than the chi-square critical value, reject your null hypothesis of no p order autocorrelation, otherwise do not reject. So that is the decision rule is as usual. That means, so if your calculated value is greater than the critical value in the chi-square table, reject your null hypothesis, otherwise do not reject. Rejection of null hypothesis means, so your model suffers from the autocorrelation problem. If you are not able to reject your null hypothesis, so then the model is not suffer from the problem of autocorrelation. So these are the steps which are involved in this BG test, Bruch, so okay, the Godfrey test or the LM test. Okay, I think that is enough. These are the two popular diagnostic tests are the detecting measures of autocorrelation. So then the last but not the least, okay, the part of our discussion is related to autocorrelation correction. So if by making use of Durbin-Watson test, or by making use of BG test or any other test, there is one more test is called as run test. So by using any of those tests, so if there is a presence of autocorrelation, then we should have to remedize that, or we should have to correct it, because if we are not corrected the problem of autocorrelation, then our results are not valid, our results are not reliable, our results are not valid, or our results are not reliable. So because of that, we need to correct it. We need to correct it. We need to correct it. So okay, we need to correct it. Okay, we need to correct it. Okay, we need to correct it. So what kind of correction we should have to follow, or what is the remedial measure, what are the correction measures? So let us have a brief discussion on that. Then I will show you in 10 to 15 minutes by taking one example of a practical problem on this autocorrelation problem. Okay, well, let us take the procedure of correcting the problem of autocorrelation with simple regression model, because this problem of autocorrelation might be in multiple regression model or also in case of simple regression model. So to simplify our analysis of correction or remedial measures, let us take a simple regression model with only one independent variable and assume that the disturbance term of this ut follows AR1 process. So that AR1 process is written as ut is equal to raw ut minus 1 plus Vt, as we already noted that. And the value of this raw is lies between minus 1 to plus 1, as we already noted that. And the Vt of this AR1 process, that is a classical error term. That means it is not autocorrelated. The idea is to remove the autocorrelation term, that is raw ut minus 1 from the error term. So that means we should have to remove this ut minus 1, raw ut minus 1 from this. So if you remove this raw ut minus 1 means the problem is corrected. The problem is corrected. But how to remove this raw ut minus 1 from this regression is the process which we needed to know for correction of this autocorrelation problem. Correction of autocorrelation problem. Okay. So to see how this is done, rewrite the earlier AR1 process as follows. So earlier AR1 process was UT is equal to raw UT minus 1 plus VT. Now I have taken that raw UT minus 1 into the left hand side. That means UT minus raw UT minus 1 is equal to VT. What this suggests is that by removing or subtracting raw UT minus 1 from the autocorrelated error term UT, we obtain the uncorrelated error VT. So this is already we have noted, it is an uncorrelated error term. So how to obtain this uncorrelated error term? Just take the difference between or subtract the UT from raw UT minus 1, that removes the problem of autocorrelation. So to correct the problem of autocorrelation, we transfer the data so as to remove raw UT minus 1 from UT. So raw UT minus 1 from UT. So then how to remove or this raw UT minus 1 from UT? So the procedure is as follows. So first we have a original equation. Earlier we have noted that is our simple regression model, yt is equal to beta 1 plus beta 2 xt plus ut. Now we have expressed the same regression with one period lag. So instead of yt, now we have written it as yt minus 1. Instead of xt, we have written it as xt minus 1. And ut, now it is ut minus 1. This is called one period lagged value of the regression. So now we should have to multiply this one period lagged value of this regression by raw. So hence yt minus 1 is multiplied by raw, beta 1 is multiplied by raw, beta 2 xt1 minus t minus 1 is also multiplied by, and the ut minus 1 is also multiplied by raw. So hence in the third step we have multiplied all the elements of this one period lagged value regression equation from the raw. The next is subtract this, that is this means above from the original unlagged regression equation, that is yt is equal to beta 1 plus beta 2 xt plus ut. So by taking the difference between these two, you would get this expression, this equation, yt minus raw yt minus 1, beta 1 minus raw beta 1, and so on. So then by making simplifications to this step, the collected terms are as follows by using that factorization or say the taking out an element, the common factors. Finally we would get a equation like this, that is yt minus yt minus raw yt minus 1. So instead of yt in your original regression model, in the corrected regression model, your dependent variable is yt minus raw yt minus 1. Instead of only beta 1, now we have beta 1 times 1 minus raw, like this. So now that the problem of autocorrelation is corrected, or we have removed that raw ut minus 1 from the regression analysis. So since we have removed that raw ut minus 1 from this regression equation, the problem of autocorrelation is corrected, because you have a new error term. The new error term is ut minus raw ut minus 1. Earlier you have shown that ut raw ut minus 1 is equal to vt. Just remember that ut minus raw ut minus 1 is equal to vt, where the ut is no autocorrelated term. No autocorrelated term. So use this to write the equality on the last side of the as like this. Instead of writing ut plus raw ut minus 1, you can represent it by only vt. So by assumption, as just I have told you, that this vt is not autocorrelated, and so above transformed model is free of autocorrelation problems. So that's why now you have not ut in your transformed model. In your transformed model, your disturbance term is vt. So this vt is not autocorrelated, not autocorrelated. So I think, did you get it? So that means first you have to estimate raw, multiply it times the lagged values of the dependent and independent variables of the model, then apply the OLS to the transformed model. That is why this is the procedure. What we have did, we have first estimated the raw value, multiply that raw with the variables, both dependent and independent variables of the model. So then we simply use the OLS estimator to transform model, because in case of this transformed model, the disturbance term is not autocorrelated, autocorrelated. And in literature, this process is known as generalized least squares method. So the resulting estimators for the previous equation is known as GLS, generalized least square estimators. These generalized least square estimators are the best linear unbiased estimators. They are not the biased estimators like OLS estimators. Earlier we have noted that the OLS estimators are not the blue estimators when there is a presence of the problem of autocorrelation. But whereas these GLS estimators are best linear and unbiased estimators because the corrected model, the transformed model is not suffer from autocorrelation because VT is not autocorrelated. So in particular, GLS estimators are minimum variance and thus are more efficient than OLS estimators in the presence of first order true autocorrelation. That's why, so if there is a presence of autocorrelation in our regression model, we have to use GLS method. That GLS method produces the best linear unbiased estimators, or in other words, so this GLS process or the GLS methodology of estimation that modify, transformed our model in such a way that the problem of autocorrelation is automatically corrected. And finally, we use again the OLS estimators to the transformed model, and 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 uh, since this is a new model and the new method of estimation, so hence we call it as a generalized method of least square or generalized least squares method. This is about the first correction method. So, but the one of the most important point which you should have to bear in your mind in use of this GLS method as a method of correction of autocorrelation is that you should have to know the value of raw, because earlier in the earlier steps or in earlier procedure you have noted that every element of your regression analysis or the regression model has to be multiplied by raw. Without knowing that raw, you cannot make use of that previous method. So that's why you can call that method as when raw is known. When raw is known. So when the raw is not known, there are different methods. So you can estimate the raw by using that earlier AR1 process. By using that AR1 process, and again you can use that. Or in practice, in the literature, one method that to estimate the raw is by making use of Cohran Orcott method. This method is called as Cohran Orcott procedure of estimating the raw. So how to use this Cohran Orcott method? So we should have to ignore the problem of autocorrelation in our regression model. We should have to estimate our original model using OLS, and from this we should have to obtain the sample residuals. And we have to assume the AR1 pattern of the autocorrelation in the errors of UT in the original regression model is reflected in the sample residuals of that is estimated y from the step 1, and that is the AR1 process. Thus, if you regress UT on UT minus 1, the estimated coefficient of the UT at T minus 1 will be an estimate of raw. That means, so we have to estimate the raw from that first order autocorrelation. But the estimate of raw from the second step is biased since it is from an autoregressive model. So because we are noted that UT is a function of UT minus 1, so that is a biased one. That is a biased one. So to reduce this bias, the estimated value of the raw from the second step is to transfer the data into a generalized difference form and estimate the resulting model. So then obtain the residuals, which we call as WT. So that means, so it is mathematically like this. We need not much worry about this mathematical derivations of this Cohn-Harcott method, because the most of the statistical packages make uses this the Cohn-Harcott method of estimation. Directly we can estimate the correct the problem of autocorrelation by using this Cohn-Harcott method, and it is an iterative procedure. So of course they are of course given in these slides. Iterative means, so by using the several steps, so that minimizes the value of the raw, that minimizes the final value of the raw, and finally we would get a final estimate of the raw. And by using that final estimate of the raw, and that has been multiplied with the values or the elements of the regression analysis, and finally we would get the results of the estimators. So this is a mathematical part of how this cone or cut method as a method of estimating raw and using that estimated raw in correcting the problem of autocorrelation. So this is about the problem of the correcting methods. Then one more method is that, so if there is a problem of autocorrelation, we can change our variables into difference form, into first difference. So by changing our variables into first or second difference, that the problem of autocorrelation can be remedied, or the severity of the autocorrelation problem can be remedied, or come down. So that is another way. That's why there is no any single rule of thumb for even correction. So there are different methods based on the data you have been selected, based on the characteristics of the variable you have been selected. So we have to use the appropriate method of correction. So this is a brief discussion related, or a theoretical discussion related to what is autocorrelation, and what is the nature and types of the autocorrelation, what are the causes for the presence of autocorrelation in our regression model, and the consequences or the implications of the presence of the autocorrelation in our regression model, and how to know whether our model suffer from the problem of autocorrelation. They are called as diagnostic tests or the detection measures. And the last but not the least is, if there is a presence of autocorrelation in our regression model, we must have to remediate this. And the last part of our discussion is related to correction measures or the remedial measures. This is about a brief discussion related to this the problem of autocorrelation. So this is about the autocorrelation problem. So now let me take one example to do this within I need, of course, only 5 to or 10 to 15 minutes to show you the use of UVs to deal with this problem of autocorrelation. So shall I continue for another 15 minutes?
Yes, sir.
Okay, sir. Thank you, sir. Thank you. Because I think I have crossed 1.5 hours of the time given by you. So I need another 15 minutes to complete this. Okay, sir. Thank you. So okay, here I make use the UVs package for this problem. Okay. 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 Oh, sorry. 1 minute, please.
Where is it? Huh?
Okay, now, so that is the home page of the UVs. Okay, now I have opening a foreign file, since my data is in Excel sheet. Okay, my Excel sheet is in the desktop. So yes, I have opened the desktop. The title of my file is book 1. Okay, book 1.
ನಂಬರ್ ಬೇರೆ ಅದಾರಲ್ಲ ಹುಡುಗಿ ಕೃಪಾ ವಿದ್ಯೆ ನಂಬರ್ ಅಣ್ಣಪ್ಪ
It is in book 1. So now I click on that. Okay, the data is open. Go to next, then next. So then finish. And okay, so this is now I have the variables. So like consumption, income, and investment. Okay, this regression, just I have take here only the two variables. That is the consumption is the dependent variable and income is the independent.
Sir, please unmute yourself, sir. Mahesh, sir. Mahesh sir, please unmute yourself, sir.
Okay. Can you hear me?
Yes, sir. And please
Okay.
repeat what you just told, sir.
Okay. So do you have familiar with these EViews?
No, sir, we have installed
Oh,
now. Yeah.
okay. Then shall I start with first?
Yeah, first, sir, when you just open the EVs from there, sir.
Okay. Then I close this. Better to close
Yeah,
this.
fine, sir.
So okay. So you have to first open eViews. Okay. Then eViews home page opens like this. So then if you are already your data in some other formats. So since I have my data in Excel, hence the eViews consider that Excel or other files as foreign files. If you are already a file within eViews, you go to the file within eViews and open there. Okay, but better to have always our data in Excel, and that can be imported into any software including eViews. So hence my data is in Excel file. So to import my Excel file, I should have to click on open foreign file. Okay. So if you just click on that open foreign file, that a new window open that asks where your foreign file is there. So my file is in a desktop with a folder name like this Davangere University, and I have to open that Davangere University file, and within Davangere University my title of the Excel file given here as book 1. Okay, so then I should have to click on that book 1. So then book 1, if I just select that book 1, the file name appears automatically. You need not to type it. Okay, then open that. Okay, so then
Yes.
click on open button. So once you just click on that open button, eViews windows opens. So within this eViews windows, your variables appears here. So for example, in case of the first radio cell, you have predefined range. Yeah, I have a predefined range because it is in terms of columns in Excel sheet. And you might have different sheets, in Excel. Your data might be in the second sheet, third sheet, fourth sheet. So then you should have to select the data which is required for your analysis in different sheets. Since I have only data in first sheet of my book 1 Excel sheet, ends it only if sheet 1 automatically appears. Otherwise, you should have to click on this downward auto mark and select the sheet where your data is. Okay, that is related, and you need not to custom range. Automatically it is selected, and you need not to do anything other than this selection of the sheet of your Excel in this first step out of the fourth step in importing Excel file to your eViews. The next is header lines. You have a column headers. Already you have a column headers because you are already given the names for your variables in the Excel itself. That's why you need not to give any new names to here. That's why do need not to make any corrections in this step 2 also. Okay, then click next. Then text representing not. So you have no text representing no na is not there. That is the number of observations are not absent in any of your data. That's why you need not to write any text here. Okay, the first name of our variable is here. That's why that is found here. So then click next. Okay, this is your final format. So the first variable is here, the second variable is income, the third variable is consumption, the fourth variable is investment. Okay, so according to our format which were already noted in our Excel sheet, hence we need not to make any corrections in importing an Excel file into eViews. Finally, finish this. This is the fourth step. So once you just click on that finish, so all your data or the variables are imported into eViews. This is work file, or the all your informations are in work file in eViews. If you want to give a name for this, you can give this. Otherwise, it is book 1 like this. Okay, then here the elements are C. This C is the coefficients which you need to estimate. So for example, if I click on that, it is 000 because yet I have not estimated the coefficients. By default it comes. That means The C is not say imported by us. The C is inbuilt, okay, element of this E views. C is the coefficients, and the consumption imported by me. If you just double click on that consumption, your data related to consumption appears here. Okay. Similarly, the income and investment and the year and the residual, it is also not available because yet we are not estimated our regression model. Okay. That's why there are two inbuilt elements already in EViews slide or EViews work file. One is C coefficients, the other one is residuals. Whatever the other elements which you have seen here are imported by yourself. If you have imported only two variables, then two appears. Since I have imported four variables, one is here, consumption, investment, and income. So hence, I have additionally four elements or four time series variables in this work file. So this is importing the data into eViews. And of course, either Prem Kumar or especially that Niranjan, as I hope mentioned this word regarding all these types of diagnostic tests, not only related to heteroscedasticity or multicollinearity or autocorrelation, the most of the, okay, the diagnostic test in case of our econometrics in particular, or the social science research in general, the research itself is called as a post-mortem type of test. Post-mortem type of test. That means the post-mortem is conducted to know the reasons for death. Okay, the reasons for death. So likewise, you cannot use these diagnostic tests. You cannot use these detection measures in econometrics without running your regression. Without running your regression. I hope many of you have already studied econometrics. With that, I am here sharing this is that if you go through any diagnostic test, so I hope the first step of that diagnostic test, you should have to first run a regression. So then if you first run a regression, then the next step is obtain residuals and so on. So that's why all these diagnostic tests are post-mortem type of diagnostic tests. So first you should have to run your regression. Then only you should have to know whether your regression model suffer from autocorrelation or heteroscedasticity. Otherwise, you cannot identify. Otherwise, you cannot detect. So because of this reason, first you should have to run a regression here. And there are different methods of use of the statistical packages for our obtaining results or statistical analysis in general. The first one is menu driven. The second one is giving commands. The third one is known as using programs or programming. The simplest one is using menus. Using menus. Okay. Let us, of course, even within using menus also, we have some shortcuts. So here I am using the shortcut. Okay, shortcut method, which save our time of typing and so on, to obtain the results of the regression. Let us assume that the consumption is a dependent variable and the income is the independent variable. So first I have selected consumption. Okay, then press control button and click invest income. So simultaneously consumption income are selected from this work file. Then click your right mouse button, click right button of your mouse. So then if you one menu appears, okay, a pop-up menu appears, and within that the first element is open. If you just put your cursor on the open, so one more right up menu appears. So I need a equation here, because equation means a regression equation. I have to run the regression equation. So that's why open as a equation. Okay, then click that as equation. So your equation dialog box open. Otherwise, you have to go to quick, then a pop down menu appears there. Then you should have to estimate equation, select. And in that estimate equation, you should have to type the name of variables if you go through that methodology. But in case of this a shortcut method, you need not to type your dependent independent variables. Just by selecting them, dependent variable by followed independent variables, and right click, select, and as a equation, automatically your variables comes to estimation equation dialog box. So then in this estimation equation dialog box, okay, this is the area which is needed for you to input your variables, dependent variable followed by the independent variable along with the constant or the intercept term of your regression equation. So, and below this method of estimations. So there are a large number of methods of estimations in econometrics which are inbuilt in all the statistical packages, including in eViews. If you just click on downward arrow mark, you would get a list of methods of estimation. By default, it is least square method, and so we need not to get into the other methods. We need not to get into other methods of estimation like a GMM or two-stage least square or arch method or like ERDL method or cointegration. Like this, these are the different methods of estimation used in different circumstances in econometric analysis. But for our analysis, we are using least square method. So which is in by default given. And after this, you just click on OK button. Okay, just click on OK button. So if you just click on OK button, the result appears in this new window. Okay, the dependent variable is consumption. The method which you have used to estimate the results of this regression model is least square method, and the date, time, all are given here, and the sample which you have been used in for estimation of this is, it is related to the actual data of consumption income and investment of Indian context from 1950 to 2011. The sample is 1950 to 2011. We have an included observation or the sample size of 62 years of data related to consumption and income. And this is our estimated results. And I hope you are already noted how to interpret these results. And I think Professor Rangappa sir has given in detail regarding the interpretations of the estimated coefficients of the regression results and validating the estimated results and so on in terms of the standard errors and hypothesis testing. So hence I don't want to get into that part. So related to my problem, that is the problem of autocorrelation. So along with these results in case of eViews and also in other statistical packages, not in all statistical packages, of course, especially in eViews, the Durbin-Watson test of autocorrelation is given at the end. Okay, the Durbin-Watson stat. Durbin-Watson stat. This is the D statistics of the Durbin-Watson statistic. So the Durbin-Watson statistic, for this estimated regression, consumption is a function of income for India for these 2 years of period is given by these results, and the Durbin-Watson value is 0.80. So from our discussion thus far in the theoretical part of our discussion, you have already noted that the estimated value of this Durbin statistic is 0.8, which is away from 2, which is not closer to 2. Since it is not closer to 2, which is away from 2, which is an indication of presence of positive autocorrelation, because which is closer to 0, hence it is positive. And since it is 0.8, which is away from 2, hence we can conclude that, or we can infer that this model or this regression results suffer from Durbin-Watson statistic. But the most of the people who are not familiar with this regression analysis who make uses this regression analysis. Hello? Hello?
Hello, sir. Hello, sir. Audible, sir. Please continue.
Okay. Somebody has intervened. Okay. Okay. So the calculated value of the Durbin-Watson statistics is 0.8, which is an indication of the presence of autocorrelation. So though your results are statistically significant, because by looking the t-value is 107, and the probability value is of that income coefficient is 0.00. So your interpretation is So your estimate, the influence of income on consumption expenditure is so significant, which is highly significant, significant at 1% level of significant. And your estimated value of the R square is very, very, very high, which is very, very close to 0.99. There is a 99% of variation in consumption expenditure is due to because of income. So these are the significant results which you have obtained for your data, but these results are not valid. These results are not reliable unless these adequacy test or model adequacy test. One among that model adequacy test is this problem of autocorrelation. So hence the Durbin-Watson test is positive, and which is away from 2, 0.8, which shows that there is a presence of autocorrelation. Hence these results are not valid. These results are not reliable. Okay, this is the use of Durbin-Watson statistic as an indication or for testing the autocorrelation. So then we can of course in our analysis even we can use the graphical representation also. So in that graphical representation, okay, graphical representation. So you go to view button, okay, click on view button. So there are different options available in view. Go to actual, fitted and residual values. Actual, fitted and residual means actual value of the y, fitted value of the dependent variable, and the error term value. That is the residual. Go to graph for this actual, fitted and residual. Okay. So now here this one is actual, fitted, green one, and the blue one is residual. So this residual shows you that so there is a presence. So up to this, of course, but onwards there is a presence. Or if you go to directly the only residuals graph, okay, residual graphs. So the residual graph only includes the values of the residuals. So now you have been observed here that so you have a continuous increasing in the value of these residuals up to this, then continuously decreases, and then increases, then decreases and increases, as I have shown in one of the slide in my previous discussion. So this is an indication of positive autocorrelation. This is the one way you can use this graphical representation to detect the autocorrelation by selecting this view, and within you actual, fitted, residuals, and within all the fitted, actual and residual graph are only residual graph. Okay, residual graph. The next is residual diagnostics. So this residual diagnostic is used for all the validation methods. It includes all the validation methods, like your normality of the disturbance term or the normality test, heteroscedasticity test, and the serial correlation test. So out of this, what we required is serial correlation test, LM test. So that is the Bruce-Godfrey test. Only Bruce-Godfrey test is given in EVUs. Okay, that is the widely used and most popular and scientific and used test in practice. That's why the serial correlation LM test is given in EVUs. So if you just select that serial correlation LM test and click on that, okay, that asks you by default it is lags you need to include 1, 2, 3, 4. So that depends upon you. So by default it is 2. I run this LM test for 2 lags. So then if you just click on that OK button, the results of this test appears like this. So in these results of the test, okay, in these results of the test, so earlier we have noted that so this Bruce-Godfrey test follows the chi-square distribution. That's why that chi-square value is given here. And also we can use the F test for this. So both we can use F test on the chi-square distribution test or the chi-square test to test the hypothesis of no autocorrelation. Earlier we have noted that the null hypothesis of this Bruce-Godfrey test or LM test or any test in general in case of autocorrelation problem is no autocorrelation. Okay, no autocorrelation. So hence the hypothesis of no autocorrelation is rejected because your calculated value of the observation n times r square, n times r square is 23. The probability of of this with the chi-square distribution of 2 degrees of freedom is 0, 0, 0. The f value, this probability is also 0, 0. So which means that you are rejecting your null hypothesis of no autocorrelation both by f statistic and also by observed r square statistic or the chi-square distribution test, and this is the based on this, okay, based on this methodology, okay, based on this regression, these results are obtained. Hence this is not much required for us, only for our conclusion, for our inference regarding testing of no autocorrelation hypothesis. These results are suffice enough to us. So the conclusion from this BG test is also that, or the LM test is also that, there is a problem of autocorrelation. So now I have shown you three methods here. One is graphical method. The graphical method also shows there is a positive autocorrelation. Then the Durbin-Watson calculated value, it is 0.8, which is away from the 2. Hence, there is a problem of autocorrelation. And more scientific and systematic advanced LM test also showed us that there is a presence of autocorrelation. Okay, this is about detecting autocorrelation by using E-views for any regression models. Okay, this is about the detecting measures. Okay, detecting measures. So then how to correct it? Okay, and for correction of this, and of course the first method, when the raw is known, you know, to know that raw, we should have to, again, we should have to do it manually, because we should have to obtain the value of raw, estimated value of the raw, multiply that estimated value of the raw with dependent independent variables and so on. Hence that is not available here. Okay, but whereas the other one, that is say that is the Kohn-Urquhart method. I have told you that Kohn-Urquhart method of procedure is available here. So I use that Kohn-Urquhart method here. So for that, okay, I click again here, estimate. You need not go back to your work file again to a new estimation. Whatever the modification you should have to, or you intend to do into this estimation procedure, there is a button in the menu of here. Okay, so just click or select on that. For example, here I need new estimation for the same variables. Then just click on that estimate. Again, equation estimation dialog box opens. So now here I made only one correction. The correction here is I have included a variable called AR. Within the bracket, I should have to write here 1, AR1. So by incorporating this AR1 into this equation specification box in eViews, it is equivalent to your Kohn-Urquhart procedure. And there is one more method, the Price-Wheaton method is also there. So they are more or less similar methods. Okay, this is Price-Wheaton or Kohn-Urquhart. Okay, Kohn-Urquhart method. So now I introduce a new variable, that is ER1 term. Okay, so then, okay, then click on the button. Okay, if you just click on that button, then this method, okay, this method or that Kohn-Urquhart method not uses the least square method. Just look here. The method of estimation is maximum likelihood estimation, not the OLS method. Okay, it is a maximum likelihood estimation method. And before getting to interpretation of these results, you better to look at Durbin-Watson statistic. The Durbin-Watson statistic is 1.9. Earlier in the original data, it was 0.8. But now there is an improvement in the value of Durbin-Watson, which is very, very close to 2. So you can write it is 2 because it is 1.986 and so on. So the problem of autocorrelation is corrected by using that Kohn-Urquhart method. Okay, so then let us of course, okay, whether really you can also You can also check with other diagnostic tests, higher diagnostic tests, residual graph. Okay. So now, so more or less it looks like this. Okay. But if you go to the residual diagnostic test, serial LM correlation test, okay, sorry, serial autocorrelation test, which is of course not available here because we have used the ARMA models of that. Okay, estimate or 1 minute. Right. Okay, here the maximum likelihood. Here it is GLS. So then 2. So sorry, I have told you that the GLS is not available, but which is available here. Okay. Earlier it is maximum likelihood estimation. It's a generalized least square method, Gauss-Newton method it is. So again, that was 1.9, it is 2. So that has been automatically it is corrected. So go to residual test, the serial correlation test with, for example, 1 lag. So you cannot reject your null hypothesis now because your F statistic is 0.13, your chi-square calculated value is 0.12. These are values which are higher than even a 10% level. Then for your transformed model, for your modified model, or for your model, your autocorrelated model, which is estimated by using GLS and which is estimated by using New West method, or which is estimated by Corner-Arcart method. So the autocorrelation problem is corrected. So both by observing the Durbin-Watson value and also by observing the Bruch-Godfrey test or the LM test. So these tests show that. So there is no problem autocorrelation after correction. So hence we can make use this okay, the GLS method or the Corner-Arcart method by introducing AR1 a term into our regression directly in E-views. We can automatically correct the problem of autocorrelation. So this is about the use of E-views for correcting autocorrelation, not only correcting and of course running regression and detecting the problem of autocorrelation and also the correcting the problem of autocorrelation. So I think I better to sum up my class, the today's class, since we have already have a class more than 2 hours. To summing up of this class, we have started with one of the most important problem faced by an econometrician in practice in use of time series data. That is the problem of autocorrelation. The problem of autocorrelation is due to because of violation of one of the assumptions of the classical linear regression model relating to the error term. So to have a knowledge on that, we have first theoretically discussed about the problem of autocorrelation, its nature and type. So then we enter into the consequences, the causes of that and the consequences of that. And finally, more technical ones are detecting measures and correction measures. And at the end, I have selected one practical problem, the data pertaining to Indian economy related to consumption and income relationship. We have first run a regression model using E-views, and by observing Durbin-Watson value and also the BG test results, the result showed that there is a problem of autocorrelation. Though our regression results are statistically significant, the coefficient is statistically significant, t-value is very high, probability values are very low. Even with all that, we are facing the problem of autocorrelation. So hence we have tested the problem of autocorrelation by using Durbin-Watson test and the BG test, and both the tests have shown there is a problem of autocorrelation. So then we have corrected that problem of autocorrelation, making some modifications using GLS and also by using Corner-Arcart method. In both the methods, the problem of autocorrelation is corrected because once we have tested the autocorrelation problem for the results of the corrected model, the results of BG test and also the result of Durbin-Watson shows there is no problem of autocorrelation. So these were the things which we have been discussed from last almost 2 hours. So with this, if you have any questions, so if you have, of course, if you have a time first, if you have any questions or clarifications or doubts, I think you can ask me. So Ragappa sir?
Sir, yeah.
Okay, sir.
Thank you, sir. Thank you for your nice presentation. Yeah, Chetan. Yeah.
So thank you, sir. If you have any doubts, please.
Yeah. Hello, Chetan.
Yes, sir. Yes, sir.
I think you have unmuted all.
Yes, sir. Anyone who has doubts can unmute themselves and speak.
Yeah. Right.
Okay, sir. Okay.
Hello.
Hello. Yes, please.
Good afternoon, sir.
Good afternoon.
Sir.
Hello. Hello. Not audible.
Yeah, I think there is some voice
net.
from our side. Yeah.
Some network problems.
That is, yeah. Anjali Ja, please ask your question. Hello.
Sir, I want the first one is that. Hello.
Yeah, yes, please.
Hello.
Yes, please.
Sir, I write it in the chat box. Actually.
Chat.
Right.
Okay. Okay, Anjali, yeah? Your name is Anjali Judge. So taking first difference or second difference? Huh? Hello?
Yeah, I think she is typing, sir. Not yet.
Okay, sir. Okay.
Anjali Ja, I think she wanted to ask and she want to write in chat box. Okay, any other questions?
Okay. Others.
By that time, if any others wish to ask question, you can ask, please. Yeah, otherwise we can end the meeting, sir. After, let us wait for another 1 minute.
Okay,
Then we
sir.
will end the meeting, sir.
Okay, sir. Okay. So, okay, I think.
Sir, anyhow, we have one more class tomorrow. Tomorrow, you know.
Yeah.
We will clarify tomorrow, sir.
Yeah.
Today we have more sessions, so we shall conclude it, sir.
Okay, sir.
Yes, and one more. I think from one participant, Samsung J7. So yes, the type like taking first difference or second difference. So depends upon if the problem is not corrected by taking first difference, then we should have to move on to the second difference. But the taking difference to our time series data has its own problem. I think the Prem Kumar will discuss the problem of taking difference in the one of the sessions. Probably on 8th or 9th. 9th, yeah, probably on 9th.
Okay, sir. Okay.
That is, though taking difference is one of the correction measures, but it has its own limitations. I think those limitations will be discussed by Prem Kumar.
Right, sir. Right. Thank you.
Okay, sir.
So,
Alesh?
yeah,
Sir, just a minute, sir. Alesh?
Okay, sir.
Please.
I take this privilege to say thanks to the resource person of today's workshop, Dr. Mahesh M., who is Associate Professor, Department of Studies in Economics and Cooperation, University of Mysore, Manasa Gangotri. Today, sir has delivered his wonderful lecture more than 2 hours on the topic of autocorrelation. It was an excellent presentation and it will be great asset to every participants, and I am sure that 100% it would be informative and productive. Thank you so much for sharing your knowledge with us. Thank you so much, sir.
Thank you, one and all.
Thank you, Alesh. And small correction, Professor.
Sir is Professor, sir, not Associate Professor.
Mahesh sir is Professor, not Associate. Kindly excuse. Anyhow, thank you very much, sir.
Thank you, sir. Thank you, sir.
Wonderful presentation. It was very good. Thank you all.
Thank you, sir. Tomorrow at 10:30. Yeah?
10:30, sir. 10:30, sir.
Tomorrow 10:30, sir. We shall see you tomorrow 10:30, sir.
Okay, sir. I think 2 classes are only mine, Allah?
Yeah.
Yes, sir.
Okay. Thank you, sir. Thank you and all, and good evening to all of you.
Yeah,
Thank you, sir. Thank you, sir.
Okay, meet you tomorrow.
Chetan, you can end the meeting.
Yeah, fine, sir. I'm ending it.